In the last lesson we talked about magnetic flux. And magnetic flux is the amount of magnetic field you get passing through a certain surface. And our surface in this case is going to be a loop of wire. Okay, and a loop of wire is useful because what we're really talking about in this unit is electricity generation. So flux is just the first step we need to get to electricity generation, and that's where we're going today. So we need to remember from our circuits unit that EMF is electromotive force. Now, we probably spent very little time on that, so let's just remember it now. Electromotive force is just another name for voltage. It's just voltage that is produced usually through induction. Okay, so in our case, whenever we refer to EMF, we're referring to voltage that's produced through induction, but really you could use it for voltage however you wanted to. Okay, so electromotive force and voltage, same thing. But the joy about electromotive force is that it comes with this fun symbol. There, voltage is just a V, but electromotive force, or EMF, is that thing. Now let me try to replicate that thing, because you're going to be doing it a lot. There you go. Get used to it. Just kidding. Usually the symbol that we're going to use instead of that really fancy E is just a much less fancy E. Or a backwards 3, as some people like to write it. Okay, so that's EMF, or voltage. Same thing. We got to remember that. So calculating EMF, we're going to have several different formulas for that, but I'm going to focus in on one of them quite a bit. So situation number 1 is, let's say you have a section of space or an area of field like this, and you get a wire like that. This is a wire, and you are moving it through the field. Okay, so this wire here, this wire, is moving through a section of field. So here's what happens. Inside this wire, you have a whole bunch of charges that are relatively stationary. They're not drifting in any direction. So here's electrons. I should have chosen a different color. There are a whole bunch of electrons. The protons are stationary, right? They can't move no matter what. The electrons, they're movable. They're free to move inside this wire. So when you drop this wire through this field, we can use the right-hand rule to figure out what's going to happen to those electrons, right? Because a moving charge, so all of these electrons are moving downward through this field. A moving charge in a magnetic field experiences a magnetic force, right? We learned that in magnetic fields. So here are these electrons. They are moving downward. Right-hand rule. Here we go. They're moving downward. Our field is pointing away from you or into your page. Okay, you're going to have to do this for yourself because I'm doing this on a vertical screen and the directions are just going to be different than what you would do with your paper in front of you. Okay, so try it out yourself as well, but you should get a similar answer. So here's mine, which means that the force on positive charges, remember that's what the right-hand rule is for, would be in that direction. So we're going to flip that around because we're talking about the force on electrons, on negative charges. And so what you should get is a force to your left. That's my left, right? Yes. You should get a force to your left. So you try it on your page. It should look like this when you do it on your page. And so you would get a force on positive charges in that direction, and you'd get a force on negative charges in the other direction. So both of us should get an answer to the left. And so what that means is that these electrons, these ones, they will start to move to that end of the wire, which means you'll get a relatively negative end of the wire on that side and a positive end of the wire on that side. Okay? Now you could connect that wire to a circuit of some kind, and then electricity would start to flow through that circuit. But for this first part, all we're figuring out is what's the potential difference between the left side and right side? How much voltage is there between the left side and right side? Okay, now, admittedly, this situation that we just discussed here is terribly rare, and we will really not be spending very much time on it at all, because you're not generating electricity this way by dropping wires through magnetic fields, right? So we're going to come to an actually applicable version of this thing, but we're going to start here. So our formula then is electromotive force or voltage is equal to V B L. Okay, where V is velocity. How quickly is that wire moving through the field? Okay, B is magnetic field. And L is the length of the wire. It's the length of the wire that's actually in the field. There you go. Okay, and then this guy over here is EMF in volts. Okay, so there's situation number one. You can create a voltage by dropping a wire, by moving a wire through a magnetic field. Okay, it's not very applicable to electricity generation. Situation number two is the one that we are going to spend most of our time on. It's called Faraday's law. So with Faraday's law, you are taking a loop of wire, and more likely a set of loops of wire, or a solenoid, and you are either rotating it in a magnetic field, you are changing the magnetic field somehow. That's generally what's going to happen. And so here's what you get. Your EMF is going to be equal to negative N times change in flux divided by change in time. When you change the flux through a coil of wire or set of coils of wire, that's when an EMF is produced. Okay, so here's our set of coils. Remember, there's the opening to the loop. Here's my magnetic field. If I change the flux by increasing the strength of the field, like that, so if I move this magnet away, I'm making the field weaker over here. That would change the flux. Making the field stronger, that would change the flux as well. I could also rotate this thing, right? Because we said that, according to our flux formula, BA cosine theta, if I change the theta part, that will also change the flux, right? So by rotating this thing or rotating this thing, that's going to change the flux as well. The last thing that can change the flux is changing the area of the coils. Right, now that's harder to do. Usually what we're working with is a set of fixed coils, and I can't make this thing bigger or smaller. Right, but there are certain situations where you have a different type of circuit, a different type of loop that has a changeable size, and so you could change that as well. Right, so if we think about BA cosine theta, if you change B or A or theta, you're going to be changing the flux through the loop. And changing flux is really what produces an EMF. Okay? You can show that yourself in class using a galvanometer. It's hard to hold up here. It's a lot of stuff for me to juggle. So you'll have to check that out live in person. So here's our formula for Faraday's law. We get an EMF, and that depends on three things. One of the things has multiple pieces to it. This N over here, this is the number of loops of wire that you're working with. Because as the flux changes through every loop of wire, you get an EMF in every loop. So this is a lot of loops of wire. I can't count them all. There's a lot of them. But this is also 3 layers of loops. So this would give you 3 times as big an EMF as a single layered solenoid with just as many, with just the same width. Okay, so the number of loops will determine how much EMF you get. So this is number of loops. This over here is the change in flux. And remember, the change in flux comes from the changing magnetic field strength, or the change in area, or the change in angle. And this last one is change in time. Now, the quicker you change the flux, however you're doing it, the greater the EMF will be. So if I can make my change in flux in 0.1 of a second, that will give me a greater EMF than changing my flux in 1 whole second. Okay, so the faster you make the change, the greater the EMF will be. Now, there's this weird negative out here that I have not talked about. That negative, it really isn't very important for our purposes right now. It reflects the fact that the conservation of energy must be happening here. Energy was required to change the flux somehow. So if I'm spinning this coil of wire inside a magnetic field, some sort of energy is required to do that. And the current that you're creating by doing that will flow in such a direction that the energy that it produces is the opposite of the energy that was required to make the change. Don't worry about that right now. We are going to talk about that a little bit more in Lenz's law. Okay? That's the next lesson. So we can combine these two things to make a new formula. But actually, let me expand Faraday's law first. So this will give us negative N, and then change in flux is final flux minus initial flux, right? So this would be flux 2 minus flux 1 divided by change in time. Now we can also expand that formula for flux, right? Because from last lesson we have a formula for flux. We'll do that later. We can combine these two things as well to form the following equation. V B L is equal to negative N change in flux over change in time. Okay, so this is the straight wire moving through a field scenario, and this is the Faraday's law scenario, the loop somehow moving in a magnetic field, or the magnetic field changing strength inside a loop. You don't need to worry about this. It will never come up in our course. Okay, so we need to expand that change in flux part of Faraday's law. Faraday's law is what we're going to mostly be spending our time on. So we need to remember what that formula is from last time, right? And so here it is. Flux is BA cosine theta. BA cosine theta. Okay, now let's look at our modifications for Faraday's law, having that in mind. So you can change 3 things to change the flux. You can change the field strength, you could change the area of the loops, you could change the angle between the field and the plane of the loops. And so change in flux could be changing the B part times A cosine theta. It could be changing the A part, so that would be B times change in A cosine theta. Or it could be changing the angle part, so that would be change in flux is equal to BA times the change in cosine theta. Change in anything is final minus initial, so if this is change in flux, that would be B2 minus B1. So you'd have B2, the strength of the field at the end, minus the strength of the field at the beginning, times the area, times the cosine of the angle. And it's the same thing for all 3 of these things. It's just that the thing that's changing is changing. It's a strange thing to say. Yeah, the thing that's changing is changing. It's true. BA. Now this last one here, this one you need to pay close attention to, because what some people want to write is BA, don't write this, BA times the cosine of theta 2 minus theta 1. But that is not correct. What we really want is the cosine of theta 2 minus the cosine of theta 1. Okay, it's subtracting the cosines, not subtracting the angles inside the cosine. Okay, if you try them both, you'll get two different answers. And the one that we want is this one. Okay, so now inside our Faraday's law formula, the flux in the situation we're talking about is going to be changing in one of these three ways. And so we're going to have to insert this piece of formula into our Faraday's law formula. Okay. There's one last thing that I want to show you here. Sometimes the information that you're given will be phrased in such a way that it tells you that the area is changing at a rate of 0.5 square meters per second, or something like that. And in that case, you don't have to think very hard about how to use that, because if the area is changing at 0.5 meters squared per second, then you could just use 0.5 square meters as the final area and 0 as the initial area and the time as 1 second. But there's another way that you can put this in here. But let's quickly, first of all, put in our new and improved Faraday's law formula. Change in BA cosine theta. Okay, so that's with the flux formula put in there, divided by change in time. Now remember that any one of those three things could be changing: the field, the area, or the angle. And so we're going to look at what does it look like if it's given to you in the area as changing at a certain rate, right? In that case, you could write it down like this: negative n times b times change in A over change in T, right? So square meters per second, that would be our rate of change of area, times cosine theta. Okay, that's totally valid. This is still multiplying n, b, a, and cosine theta, and it's dividing by change in time. It's just changing where you're putting that divided by so that it matches the information that you're given. Or you could rate of change of the magnetic field. That works as well. So that would be E equals negative n times change in B over change in T. That's the rate of change of the field times cosine theta. And you could do the same thing for the angle, or for the rate of change of the angle. Just probably that will not come into play. Well, you can do it anyway. Let's try a couple examples here. A coil with 25 loops makes an angle of 90 degrees with a magnetic field of 0.085 teslas. The coils have an area of 0.6 square meters, don't have to calculate that, that's nice, inside the magnetic field, and it takes 0.0355 seconds to rotate the coils 40 degrees. What is the induced EMF? Okay, so let me draw a picture of what's going on here first. So here's our coil. I'm just going to draw it as a flat coil like this, but it's got 25 loops. Okay, so they're all stacked on top of each other. To make sure that we put all the numbers in the right place, I want to point out that this is the normal line, right? Because our angle that we put in, the theta part, has to be the angle between the normal line and the field. Okay, so it starts off with the coils making an angle of 90 degrees with the magnetic field. Okay, so just to be clear, the loops themselves are making an angle of 90 degrees with the field. So that tells me that the field is making an angle of 0 degrees with the normal line. Does that make sense? The loops make an angle of 90 degrees with the field. So that looks like this. Here's our loop. Field. That's 90 degrees. So that corresponds with our normal line. So here is our original position of the field, like this. Okay, that's our original field. And then it says that the coils rotate 40 degrees. Now, it doesn't really matter which direction they rotate. The change is going to be the same no matter what. So there's our original. And then it says that the coils rotate 40 degrees. It's not the field that rotates 40 degrees. And this is a more practical situation, because usually that is what's going to happen. You've got a stationary field and you've got loops spinning, or a coil of wire spinning inside the magnetic field. Okay, but here's what happens when we rotate the coils 40 degrees. So this is our normal line, remember that? And we are rotating that normal line 40 degrees. So now our normal line, sorry, I have to cock my head to properly draw this, is over here. Okay, so we've rotated it 40 degrees. So our loop is now oriented, oh boy, let's see if I can do this. Our loop is oriented like this instead. Okay, but the loop part, that doesn't really matter. That's kind of just messing up my diagram over here. So I'm just going to leave the normal line in there, because that's what we're measuring from anyway. So now the question is, what is the new angle between the field and the normal line? It used to be 0, right? At the very beginning, the field was perpendicular to the loops, which is parallel to the normal line. So 0 degrees, that's the original. And then we rotated the loops, and thus the normal line. We rotated those 40 degrees. So my original angle was 0. Now it's 40 degrees. Okay, so theta 1 is 0, and theta 2 is 40 degrees. So we have to be careful about the information that's given to us over here. We have to make sure that you are putting the correct angles in there. So I highly recommend, yet again, drawing a diagram. Okay, so here's the situation we find ourselves in. Oh, I do already have purple. Great. I'm trying to figure out what the EMF is. And it's negative N times change in flux divided by change in time. And the thing that's changing here is the angle. So we've got our EMF equals negative times N, B, A, and then the change thing, cosine theta 2 minus cosine theta 1. And all of that is divided by the change in time. Okay, so this is the version of Faraday's law that we need for this situation, because it's the angle that's changing. And then, now that we've done our diagram and we've figured out what theta 1 and theta 2 need to be, now we can just put all the numbers into the formula in the right place. N is 25. B is 0.085 Teslas. The area is 0.6 square meters. Okay, conceivably it could give you the dimensions of the loop, and then you have to figure out the area of the loop and put it in there. But that's going to be rare when you're working with a formula this big already. And then we're doing the cosine of theta 2 was 40 degrees minus the cosine of 0 degrees. And all of that's divided by the time that it took to do that, which was 0.0355 seconds. Okay, make sure that your calculator is in degrees and not radians, otherwise you will get a different answer. So you should get, try this yourself, you should get 8.4 volts. And that voltage works out to be positive. Okay, we had a negative sign up at the front, and if you do cosine 40 minus cosine 0 over here, you'll get a negative number. And those two negatives end up canceling each other out, and you get a positive voltage. But for this course, I don't really care if you include that negative or not. The purpose of that negative, we're going to address that when we do Lenz's law. And so it's not really my goal for this particular section to make sure that you've got the negative or you've not got the negative. Okay, what we are really more interested in for this thing is the magnitude of the voltage, the magnitude of the EMF, and not that negative sign. Part 2. A metal rod slides along two conducting rails connected to a light. the area changes at a rate of 0.625 meters squared per second. Ooh, that's a rate change. That's a rate of area change question. So we're going to have to use one of those versions of the formula that's a rate version. A magnetic field of 0.8 teslas is perpendicular to the plane of the loop. Okay, perpendicular to the plane of the loop means along the normal line, right? Which means 0 degrees. What is the induced EMF? This is a strange situation, so I want to draw it out for you. You've got two conducting rails. Let's say like this. Here's conducting rail number 1, conducting rail number 2. They're connected to each other, I suppose. And then we're going to connect them to a measuring device. There you go, there's our measuring device. Okay, and then this is made into a circuit using a rail. So here's our metal rail. Whoa! Let me try that again. Let's try to make a straight rail. That'll do. So here's our rail, and we are moving the rail, let's say this way. It says it's changing at a rate of 0.625 square meters per second. We don't know if it's increasing or decreasing by that much. I mean, you can assume that it means increasing, I suppose, because otherwise it might say negative 0.625 square meters per second. But for the sake of the diagram I just drew, we're going to say it's decreasing. But again, it doesn't actually matter. Then we've got our field. Our field is inside this thing. And so, where the rail is at the very beginning, you've got a certain area. And this is saying that as you move the rail in the direction I've indicated over there, you get a change of area of 0.625 square meters per second. Okay, and so the size of the loop is changing. Again, this is a really rare situation, and so it's just not going to come up very much, but it's possible. And we deal with all sorts of possible things in physics. And so we're asked for the EMF. That's negative NB. And then let me put in the version that uses the rate of area change, or rate of change of area. It's just so many ofs in that sentence. Times the cosine of theta. So there's your area change formula. And so we get negative N. How many loops is this? Just one, right? It doesn't say that there's a set of loops of wire that are all changing size. So it's really just one loop that's changing. And then it tells us our field strength is 0.8 teslas. And then it tells us that the area is changing at 0.625 square meters per second. So that's 0.625 square meters per 1 second. And then this says that the field is perpendicular to the plane of the loop. And again, that means parallel to the normal line. So then we would have the cosine 0 degrees. Okay, and when you calculate that out, you get an EMF of negative 0.5 volts. I said before that I'm not really concerned about the negative. I'm really just concerned about the magnitude of the voltage. And so having an answer of 0.5 volts rather than negative 0.5 volts, I will find completely acceptable.